Okay, so we're going to work with A1 for 2 days. Some basic vocab for matrices that you should be familiar with so you know what I'm talking about when I say these words. Matrix, number one, it's just a rectangular array of numbers in different rows and columns. When I talk about matrices, the first time in Algebra 2, I usually tell students to think about an Excel spreadsheet. I mean, you've got rows and columns, and numbers go in the different rows and columns, and that's basically what a matrix is. Every matrix has something called an order. And order, another word that I often use and interchange with order is the word dimension. And we list dimensions like m by n, where m is always the number of rows and n is always the number of columns. So you might also write down in your notes rows by columns. That's how you label the dimensions or the order of a matrix. And then also I'll be referring to entries in a matrix. So an entry is just a specific number in a specific row and column. So if I said, what's the entry in the second row, fourth column, everybody knows where to look and we're all looking at the same entry. So on this first example, I don't know that you necessarily have to write these matrices down. What I'm more of thinking about you doing is having a conversation with your small groups to name the order of the matrices, and then we'll put those orders up on the board and talk about some special names. Okay, so I've got A through D on this slide. If you could just have a quick conversation, can you list the order of the matrices that you see in A through D? Go ahead, Chapter.
Yeah. C is 2 by 2. I get confused which one is rows.
I just have to remember columns. I feel like rows can be either way.
Okay, so I'd like for you, when you see a direction like state the order of the matrix, for you to be thinking about m by n, row by column, what's the order of my matrix. Maddie, what'd you guys say for A? 1 by 1. Okay, 1 row, 1 column, and there's 1 entry. Okay. All right, Melissa, what'd you guys say for B? 1 by 4. Rows are horizontal, so we have 1 horizontal row, and then we have 4 separate columns. A 1 by 4 matrix has 4 entries. This matrix has a special name because it's just 1 row. It's called a row matrix. You could imagine there's also something called a column matrix that is a single column. All right, Eli, what did you guys say for C? 2 by 2, excellent. Anytime the rows equals the columns, we call that a square matrix. And in this matrix, we might also refer to it as a zero matrix because all entries are zeros. Yeah. 2 by 2 has 4 entries. All right, and the last one. Let's see. Campbell, what did you guys say for D? 3 by 2. Okay, so count your rows. There are 3 horizontal rows, and there are just 2 columns. How many entries are in the 3 by 2? 6, right? The number of rows times the number of columns gives us the number of entries, so there's some connection there. Excellent. All right, we're going to talk about something that you haven't probably seen before if you're coming from Algebra 2. That's called an augmented matrix. So you did like a very surface level, sort of ACT prep version of matrices back in Algebra 2. If you're coming from Algebra 3, you should have had a matrix chapter, so some of this stuff may be a repeat of what you've seen before. An augmented matrix is a matrix that represents a system of linear equations. we're doing chapter 8 right after chapter 7. Chapter 7 was basically all about systems. Systems of equations, systems of inequalities, writing systems for linear programming. And now matrices is going to take a second look at these systems and give us some additional solving methods. Okay, so I've got a 3-variable system here. X minus 4y plus 3z equals 5. Negative x plus 3y minus z equals negative 3. And 2x minus 4z equals 6. I'm going to write it as an augmented matrix. So looking at that system, how many rows do you have? 3 rows. How many columns? 4 columns. 1 for the x, 1 for the y, 1 for the z, and 1 for, I'll call it your constant. Okay, so we need to make a 3x4 matrix. Now remember, a matrix is a rectangular array of numbers in rows and columns. So what we're going to put into the matrix is just the coefficients for these variables. So in that first row I could do 1, negative 4, and 3. And then I'm going to use a colon to represent like that equal sign, and I'll put my constant on the other side. The book will use like 3 dots, 3 vertical dots. I just think that's extra dots to make, so I'll just do 2. Okay, and then I could do the second equation. That's negative 1, 3, negative 1, and negative 3. And then in the last one, because you don't have a y term, what do you have to put in that entry? A 0, a placeholder for that y. So 2, 0, negative 4, and 6. So note that everything is really super organized in my matrix. All my columns represent something specific in the system. The first column is the x's, second column is the y, third is the z, fourth is the constant. And then on the rows, if you think back to chapter 7, we would treat those like the different equations. Row 1, row 2, row 3. Now I'm just going to put a brief side note here. This is called an augmented matrix, and we're going to be working with this in section 8.1. There is another type of matrix that we'll be using to solve systems. It's called a coefficient matrix. And we will be writing coefficient matrices to solve systems. And so in the coefficient matrix, you only want coefficients for variables. So we're going to leave out the constants in a coefficient matrix. So if I were asked to write the coefficient matrix, I would do a 3x3. So just kind of be aware that, like, it depends on what the directions say, right? Augmented matrix or write a coefficient matrix, okay, or what solving method you're using. Okay, we're doing okay so far? Now, I have 2 examples on the next slide, and they actually come from your textbook in the same section where your homework is. So what I did was I gave you the page number and then like the number of the problem. That way, if you don't want to write down the original problem in your notes, because like writing the system or writing the matrix sometimes takes a while, you can just write down the page and the number. You can do the answer in your notes, but then you can always refer to it in the textbook if you need to. So I've got 2 problems. They come from page 547, and it's number 20 and also 23. So this is page 547, number 20 and 23. And I'll give you a little bit of time. So in the first one, you're going to write the augmented matrix. In the second one, you're going to go reverse. You're going to write the system of equations represented by the augmented matrix. Now, the textbook and the directions will say use X, Y, Z, and W. It just depends on what your augmented matrix is, how many of those coefficients you'll use. But you know how we did a 3x4 for the 3-variable system? You may see some 4x5 matrices, and so you need another variable. So we go back to W. It doesn't really matter what letter you would put. Letter is arbitrary.
Please excuse this final interruption. Our College Career and Academy Expo is now concluded. All sophomore students should be in their 4th hour classes in the next 5 minutes. Thank you for everyone's assistance and flexibility today. Have a good afternoon.
Okay, so these are my answers. I'm taking a system and writing an augmented matrix. So I've got those colons separating my coefficients and my constants. And then I've got a system of linear equations. Because I only have two numbers on the coefficient side, I'm only going to use up x and y. So it must be x plus 2y equals 7 and 2x minus 3y equals 4. How are we feeling about this? Anybody got any questions for me? Okay. So we're going to talk next about something called row operations. And we call these elementary row operations. You basically have three things that you can do to different rows in a matrix. Okay. These are your elementary row operations. The first bullet point is interchange two equations, which are two rows. That means, like, if I want the third equation or the third row to be the first row, I could just swap them out. Okay, that's totally allowed. So you can move rows up or down, just move the other row accordingly. So that's bullet one. Bullet two, I can multiply by a non-zero constant. We would refer to that as a scalar. I mean, obviously you don't want to multiply by zero because then everything turns to zero and there's nothing interesting about that. But your scalar can be all types of numbers. It can be positive numbers, it can be negative numbers, it can be regular small numbers, it can be big numbers. So I can multiply each row by 100, I can multiply each row by -2, and I can multiply by fractions. So I can multiply the row by 1/3 or 1/100 if I wanted to. So you're unlimited in your choice of scalar besides 0. Okay. And then 3 is basically add or subtract rows. But it does say you're allowed to add a multiple of one row to another row. So just know, like, you're combining the scalar and addition in one step. So it's like, what if I want to multiply row 1 by 2 and then add it with row 3? I could do that all in one. And so it kind of reduces the amount of work that you have to do. Other than that, I would say don't try to do too many row operations at once. Then it gets too confusing. So it's just kind of like choose one row at a time. Okay, now you're going to be using row operations to get things in something we call row echelon form. And we can abbreviate row echelon form REF. Row echelon form. Okay, so there are like 3 characteristics of row echelon form. The first characteristic is not common for us here in honors pre-calculus. We're not going to see this a lot, but if you happen across a row that's all zeros, put it at the bottom of your matrix. second one says all the other rows will have their first non-zero entry be 1. Okay, so think about a row. A row is horizontal. In the matrix, you would have different numbers in that horizontal row. The first number that shows up that's not 0 has to be 1. So it either has to start with 1, or it's 0, 1, or 0, 0, 1, or 0, 0, 0, 0, 1. Right? The first number that's not 0 is 1. And I'll also draw a picture of row echelon form once we get this third one down. And then the last characteristic is for those ones, the higher up you are in the matrix, the further to the right your 1 is. Okay, so the ones, as you go down your matrix, they need to move at least 1 entry to the right. Okay, so I'm going to draw an example of a row echelon form. That looks like row echelon form. So I don't have a row of all zeros, but if I did, it would be at the bottom of my matrix. For all my other rows, the first number in the row that's not 0 is 1. And then my 1s, as I go down the matrix, they're moving over. Okay, so the 1s are never going to be in the same column. Okay, so they always have to move at least 1 over to the right. Okay, so the higher up you are, the more to the left you are. You can sometimes see if your thing is in row echelon form. Some people look for a triangle of zeros down there. So everything down there before your first terms have to be zeros, and then they kind of have to form a triangle. It has to be slanted, because then that means it's moving over. Okay, and then before we get into what we're going to do with the row echelon form, we got one other thing. It's called reduced row echelon form, RREF. And RREF is when your zeros, your leading ones are, before them are all zeros and after them are all zeros. So basically your matrix has only zeros and ones in it, and every row is only allowed 1, 1, 1. So I'll draw an example of that. That would be a reduced row echelon form. Each row has only 1, 1. Before and after the 1 are only zeros. And my 1s are moving over at least 1 to the right as I go down the matrix. Okay. Now notice here I didn't put a 1 in that third column. There very well could have been a 1 there and then a 1 in the last one. So sometimes you get a diagonal of 1s, but it could move over further. And then I have a 0 row. Now, a lot of times I'll be asking you when you're solving systems to put it in row echelon form. But when you're doing it by hand, I probably won't often ask you to do reduced row echelon form because that takes more steps. Okay, so we're going to practice today doing a row echelon form, the one above. Okay, so here's the problem that we're going to work on. It's example 4 from page 541. I would write down the matrix in my notes for this because we're going to do different things to it. So today, when you do these problems in your homework assignment, they're going to tell you what to do. So they're going to give you the row operations that you should perform to get to row echelon form. Tomorrow, we take away the hints. So we just give you a matrix and we say, put it in row echelon form. You have to come up with what you're going to do. Swap rows, add rows, multiply. So as we kind of work through this example, I'll be talking about in context of like how you'll be thinking tomorrow when you're on your own and you don't have the hints. Okay, so before I get into that first bullet point, what they're telling me to do, I'm just going to look at my matrix right now. Are any of the rows good to go for row echelon form, as is? First row. First row has a leading 1, okay? And it's already at the top of my matrix. If it were down on the third row, I would swap rows and move it up to the top. Okay, but it's already at the top of my matrix, so I don't have to do anything to row 1. So for me, if I'm thinking about my goal is to get row echelon form, row 1 is done. Okay. So on the next line, I would copy my matrix, and I would only copy row 1 for right now. And then I will tell you, like tomorrow, I usually try to work down, like I try to fix row 2, and then I try to fix row 3. I don't try to do row 3, then row 2, because that can sometimes get you in trouble. So, row 2 is not ready for row echelon form, right? What has to be true about the first entry in row 2 in order for it to be in row echelon form? It has to have a 0 so that my leading 1 can move over 1. So when you're looking at your different rows, you could get a 0 very easily, right? Add row 1 and row 2. So that's what they're telling you to do here, but that's why they're telling you to do it, to get a 0 there. So that means row 3 is unchanged for right now. Okay, so I'm going to leave row 3 as is. When I do my work with this, I'm always going to write what I'm doing to the row off to the side. So I'm going to copy that row 1 plus row 2 over there. And then you have to look at the matrix above and do the work. So 1 plus negative 1 is 0. Negative 2 plus 3 is 1. That makes me extra happy because now not only do I have a 0, I have a leading 1. That doesn't always happen, but that's good for me. 3 plus 0 is 3. And 9 plus negative 4 is 5. So now I'm really pleased because I got the 0 and I got the leading 1. So row 2 is ready to go, right? Got row 1, got row 2. Now I need to work on row 3. Okay. So usually when I'm trying to do my row and get into row echelon form, I'm going to focus on getting these zeros first. So I currently have a 2 in row 3. How could I get that 2 to be 0 using my other rows? Multiply row 2 by 2. Multiply row 1 by negative 2. And then if I were to add it to this row, it will come out to be 0, right? Which I need a 0 there. And that's really the only way I'm going to get a 0. So that's going to be the next step that the book tells you. Okay, add negative 2 times the first row to the third row. Now, when you're looking in your book and you're doing these homework problems tonight, it should say something about you're doing it to the second row, to the third row. So that's like a good, like, that's the row I'm changing. Okay, so then if I'm doing it to the third row, I'm going to keep the first and the second rows the same. I don't have to do any thinking, just copy that down. And then it's going to be the third row. I'm going to do negative 2 times row 1 plus row 3. Now remember to do that, you go back up to the previous matrix. Not the original matrix, just to the one right above it. So, negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times negative 2 is positive 4, plus negative 5 is negative 1. Negative 2 times 3 is negative 6, plus 5 is negative 1. And negative 2 times 9 is negative 18, plus 17 is another negative 1. So I'm less pleased with that outcome because I didn't get an extra 0, and I don't have a leading 1 either, but at least I have that first 0, right? And now, how can you get your second 0? Add row 2 and row 3. Okay, so that's going to be the next direction. Add the second row to the third row. So again, we're always changing now this third row because we're happy with row 1 and row 2. Go to the matrix right above. 0 plus 0 is 0. 1 plus negative 1 is 0. And we get a 2 and a 4. Okay. I'm getting closer. Well, we're not in row echelon form. What has to be true of row 3 to be in row echelon form? You got to have a 1 at the front. So what's a good way just for us to change row 3? Multiply by a scalar 1/2. Yeah. So remember, your operations are switch rows, add rows, multiply rows, or multiply by scalars, I should say. Okay. I'm going to do 1/2 times row 3. That's going to be 0, 0, 1, and 2. Now I'm happy, I'm pleased, it's in row echelon form. I got my little triangle of zeros right here, and my 1s are leading every row. Looks good. Okay, now let's just put a little bit of context to like, why are we doing all this? Why are you making me write a matrix 5 times, Miss Chonky? I'm tired. Okay, that kind of stuff. Do you agree that up here at the beginning, this is a system? It's an augmented matrix? So this is like x minus 2y plus 3z equals 9, negative x plus 3y equals negative 4, and 2x minus 5y plus 5z equals 17. And we know how to solve that from chapter 7. Label my rows. I got one row with x and y in it, so I'm probably going to do row 1 and row 2 to cancel, or row 1 and row 3 to cancel z, and then do elimination again. And then once I get one of my variables, I'll plug in and solve, and then I'll plug in again. Remember all that? Mm-hmm. Okay. All right. Once you get things in row echelon form and you don't mess around with all those x's, y's, and z's, in row echelon form, this is the same system rewritten. X minus 2y plus 3z equals 9. Y plus 3z equals 5. And z equals 2. Easier to solve now? Z is 2? 3 times 2 is? 6. Subtract the 6 over. Y is? Negative 1. That would be plus 2, plus 6, so that's x plus 8. Subtract 8. That would be your order triple. Your answer for today is going to be this. Your answer for today is the reduced, or is just the row echelon form. But where we're going with this is, then you rewrite it back as a system, and your system is super easy. It's just back substitution. Does that make sense? Does anybody have any questions about that? Hannah.
For the one where we had negative 1, and negative 1 at the bottom,
Mm-hmm.
was the second row 0, 1, 3, 15?
5.
Oh, 5. Okay.
Yep. Any other questions you've got for me? Now, of course, you're working in the matrix chapter, so I'm going to make you do the matrix work, right? But what we'll come to at the end of chapter 8 is like, now you have algebraic ways to solve systems. You have matrix ways to solve systems. We'll be doing some systems in your calculator with matrices. So like you could take your pick in a future math class or on the ACT or wherever you're at. If you're asked to solve a system, you got this handful of ways to do it. Do it the way you want. But for right now, do it like matrices. Okay, so your homework assignment is on your gold sheet. It's also up here at the board. Bring your graphing calculator tomorrow because we're going to do some matrix work in the graphing calculator.